If you've ever wondered why divers need safety stops or why your tank pressure drops when you enter cold water, then this is the video for you. The answer is not luck or mystery, it's physics. In our last episode of SCUBA Science, we discussed Boyle's law and Dalton's law and how depth affects pressure, volume, and density. In this episode, we're going to discuss two more laws of physics, Henry's law and Charles' law. These laws explain what happens to the gas inside your scuba tank and inside your body. They explain decompression sickness and also how temperature can affect air pressure. And yes, there will be some formulas in this episode, but don't worry, we're using them to make this concept easier to understand, not harder. Let's start with Henry's law. Henry's law states that the amount of gas dissolved into a liquid is directly proportional to the pressure on that gas. In formula form, it looks something like this: C equals K times P. In this formula, C is the amount of gas dissolved into the liquid, K is a constant, and P is the pressure of the gas. In diving terms, this means that the more pressure the gas is under, the deeper you go, the more gas will dissolve into your tissues. For recreational divers specifically, this refers to nitrogen. A very good everyday example of Henry's law is a bottle of soda. When the bottle is closed, we do not see any gas because all the gas is dissolved into the liquid under pressure. It's only when we open this bottle and the pressure inside the bottle equalizes with the pressure outside that the gas will come out of solution and bubbles form. Your body behaves in a similar way with nitrogen when you scuba dive. As you descend and the pressure around you increases, the gas that you breathe dissolves into your tissues at that pressure. Once your body is saturated, no more gas will dissolve into the tissues, but when you ascend and the pressure around you drops, the gas will want to come out of solution and form bubbles. From our last video about Boyle's law, we know that here at the surface, the pressure is 1 bar. When we go down to 20 meters, the pressure is 3 bars. Using the formula again, C equals K times P, when the pressure triples, the amount of gas dissolved into your tissues logically also has to triple. So at 20 meters, your body can absorb roughly 3 times as much gas as it would at the surface. While you stay at depth, this is not dangerous because the gas stays dissolved into your tissues. The nitrogen stays dissolved in your tissues as long as the pressure stays high. The real problems can occur when you start your ascent and the pressure around you drops. If you ascend slowly, then nitrogen will have the opportunity to work its way out of your body at a slow rate, not causing too many problems. But if you ascend too quickly, bubbles might form and they may cause some serious damage. And this is what we would refer to as decompression sickness. It is not caused by nitrogen being toxic, for instance, it is simply caused by Henry's law and the fact that gases dissolved into your tissues under pressure will want to come out of solution as you ascend and the pressure around your body decreases. Another very simple example relates to safety stops. Here at the surface, the pressure is 1 bar. At 20 meters, the pressure is 3 bars, and at our safety stop depth, 5 meters, the pressure is 1.5 bar. If we ascend from 20 meters directly to the surface, the gas will expand by a factor of 3. But if we ascend to our safety stop, 5 meters, the gas will only expand by a factor of 2, giving it time to work your way out of the body before we make the rest of the ascent. That is how safety stops correlate directly to Henry's law. Before we move on to Charles' law, let me quickly tell you about one of our partners, Divevolk. Divevolk produces housings for smartphones, and if you do watch our episodes, you see that I actually use them regularly as well. They're great for taking quick pictures underwater, even shooting video. I even use them for watching videos during long decompression times because in the back of the housing is a fully flexible screen that allows you to use the touch screen of your smartphone. It's super durable and fully waterproof, and you can actually use most features on your phone during the scuba dive. This is a great way to start practicing underwater photography and videography without breaking the bank and buying an underwater camera. So if you are interested in picking up a Divevolk housing, I'll put a link below. You actually get a discount on the product, and it does also support the DiveSAGA channel and SCUBA Science. Now let's talk about temperature. Charles' law says that the volume of a gas is directly related to its temperature, so long as the pressure stays constant. Or similarly, that the pressure of a gas is directly related to its temperature, so long as the volume remains constant. The formula looks something like this: V1 over T1 equals V2 over T2. V1 being the initial volume and T1 being the initial temperature in Kelvin, V2 being the volume after the temperature change, and T2 being the temperature after it has changed. When we bring this to scuba diving, this formula mostly relates to what happens to the gas when it is in your scuba tank and the temperature around you changes. You've probably seen this example with a balloon. When we fill up a balloon to a certain volume and place it in a freezer, giving the gas time to cool down, the volume of the balloon will shrink. This happens because the balloon is a flexible container. If we would place that balloon out in the sun, it would expand, assuming that it would not explode. Scuba tanks are rigid containers and cannot shrink or expand significantly, but the temperature, of course, still has an effect on the gas inside. Scuba cylinders in cold environments will not shrink, but the gas pressure inside may decrease. Scuba cylinders out in the sun will not expand significantly, but the pressure of the gas inside may increase. Here's a practical example. It does involve some numbers, but maybe it helps you understand. Let's say that your scuba tank is filled at 30 degrees Celsius to a pressure of 200 bar. First, we convert Celsius to Kelvin by adding the number 273. So 30 degrees Celsius becomes 303 degrees Kelvin. Now you enter water that is 10 degrees, which is 283 degrees Kelvin. As mentioned earlier, when the tank volume stays the same, we can replace the V for volume in the formula with P for pressure. P1 over T1 equals P2 over T2. Now we simply insert the numbers that I just mentioned. 200 bar divided by 303 degrees Kelvin equals our second unknown pressure divided by 283 degrees Kelvin. Now all we have to do is solve for P2. And P2 equals 200 times 283 divided by 303. This should mean that P2 equals 187 bars. So what that means for you, the cold water diver, is that even though you started your dive with 200 bar and a full cylinder, once you enter that cold water, you are actually only having 187 bars at your disposal. You did not lose these 13 bars, but the gas simply got colder, shrank, took up less space. That is Charles' law in action. Charles' law also works in the opposite direction. In other words, if a scuba cylinder is heated up after filling it, then yes, the pressure reading may get higher, but I would strongly advise against doing this to get a larger air supply, because this increased pressure can of course pose a danger to its structural integrity. This is, for instance, why most scuba divers will probably not want to leave their full scuba cylinders in the trunk of their car on a hot summer day. More heat means more pressure means more stress on the scuba cylinder. Again, that's not some kind of superstition, that is Charles' law at work. So combined with our previous video of scuba science, you now have the 4 major laws of physics at work during scuba diving: Boyle's law, Dalton's law, Henry's law, and Charles' law. And all of these laws shape the actual reality of the gases on our body and on our equipment while we scuba dive. It's not magic, it's not fantasy, it's not superstition, it's just a great example of scuba science at work. If you're into scuba diving, make sure to also follow the DiveSAGA Dive Debrief podcast. You can find it on Spotify and YouTube. In this podcast, we cover the behind the scenes of our DiveSAGA episodes.